It's the second of our training courses, and today we're going to be looking at inks. And one thing I think that's important to say from the outset about inks is that printers treat inks as a commodity. I mean, like, they just go out and they just get the cheapest quote. They go to Flint, they go to Sun, they go to Marabou or whoever, and just get the cheapest quote. So that's how they kind of treat it. They don't treat it like what it is. It's a very complicated system. It needs to work exactly with the press that you're working with at a certain speed. It has to stick to a certain substrate. It has to perform not only on the press, dry very quickly at high speeds, but after the press. So think about what a label goes in a shampoo bottle. It's got to stay on in your shower. It's being attacked by sunlight, it's being attacked by moisture, being attacked by people rubbing it. It's being in the supply chain. It's going to be in a bottling line. It's going to be in a canning line. It's going to be scraped and abrased. So the first thing about ink is it's a very complicated system, and it's what we're seeing more and more now is that more the bigger converting groups, people like OPM and these two guys, are now, rather than going between suppliers week after week on a cost basis, are now saying, okay, it's a really important part of our business, so we're going to have a long-term supply contract. So very often you'll find people like Zell and Gamellin or Sun Chemicals, Seedwork, will actually put a technician into a printer and they will run the whole ink operation. So it's more expensive. In other words, you're paying for service, not for the inks. What it does mean is that you're much more likely to get consistent inks, much more likely to make sure it works on the press without having to stop it or jobs coming back. So let's just start off with saying about inks. The most important thing about ink systems is that they follow the printing process. So the characteristics of each ink follow the characteristics of the printing process that it's designed for. So it may kind of seem like an obvious thing to say, but one thing that you'll find in this kind of course of educational kind of course that we do, training courses, is that you'll keep hearing the same things from different angles. Okay, so it's not a massively complicated industry, everything kind of linked to everything else. So, for example, in a future training course, we're going to look more in detail about what Flexo is, what Gravure is, letterpress, but we have a basic understanding of that to understand how the inks are made and how they flow and the characteristics of the inks. So, the most important thing about an ink is that obviously it has to run onto a press, it has to dry very quickly. You talk about speeds up to, that's 200 meters a minute, 150 meters a minute. And those inks have to dry between the time that it's the first printing station to the next print station. So that's kind of, you see the press, right? That's that fast, 200 meters a minute. So it's got to dry somehow between there and there. Otherwise, what's going to happen is that like watercolor, you're going to lodge it onto a colour, it all starts to kind of spread around. So it's really important that the inks are able to dry super quickly. So that means we have to talk a little bit about curing systems, about drying systems, although again in a later training session we'll talk more in detail about the drying system. Like I say, everything's kind of tied in and we'll keep kind of coming back to how these things work together. So ink. So the first characteristic about an ink is called its viscosity. Okay, now what that means is whether it's a paste or if it's like a free-flowing liquid, and that will depend upon the print process that it's going to be used for. So we have Flexo, we have Gravure, we have Offset, we have letterpress, we have screen, we have inkjet, and there are different ways that an ink can dry or cure. So chemistries are water-based ink, solvent inks, and energy-cured inks. And these are ultraviolet, LED, and EB, electron beam. And there is an absorption, and that's simply an ink being absorbed by a material. So if you have like a carton board or like a uncoated paper, the ink's just going to dive into it.
So what do newspapers use?
That will be generally most newspaper stocks now are coated.
But it still comes up.
Yeah, so they've got a coating on them. So in the old days, ink just used to absorb straight into the newspaper, the actual pages. So that's what came off the ink in your hands. But does that answer the question?
Yeah.
Right. So these ink systems can be any one to make things even more complicated. Each one of these ink types for each process can be any one of these types of drying process. So if we look at the process, and again, a lot of you will be familiar with the printing processes. Let's briefly go over them and then explain how they affect the kind of ink that's going to be used. So we'll start off with Flexo, which is the most commonly used printing process in the industry in Europe and America, but not in Asia Pacific, where it's letterpress still. So Flexo, what the Flexo process is, you'll see that. Okay, so you have like an ink tray. So imagine the presses that you see in Laser Expo. You've got the printing unit, you've got the ink tray, and then you've got a roller, that rotates in the ink tray, and that delivers the ink onto the Analox roller. The Analox roller is a roller like pitted surface with little like microscopic cells in it. So what happens is the ink fills up those cells, and then from there goes straight onto the plate cylinder, and then onto the material. Okay, so it's a very simple process from the ink here onto this roller, onto the Analox, onto a plate, and onto the material. There's an impression roller here just holding the material tight. So that ink needs to be able to flow really easily between there, be picked up by that rubber roller, straight onto that Analox roller, onto the plate. And when it's on the plate, it affects the plate, it's like a potato printing, and up, so it needs to go onto the surface of that dot and then be transferred onto the material. So it has to flow, and that means it's a very low viscosity, which means it's almost like water. The Flexo ink is almost like that kind of consistency. Okay, offset printing. So an offset ink is very like a paste. So where is offset used? Offset is mainly used for sheetfed labels. So it's mainly used for sheetfed presses. It's also used for very high quality self-adhesive labels. So Nilpida, Rotec, these guys. So offset is quite an important part of the industry, certainly for the wet glue labels, but also for the high quality, high end self-adhesive labels. So big players there, Nilpida,
Kodi-Mag and Wine Levels as well.
right, yeah, Kodi-Mag, and all those guys, like Kodi-Mag and Iwasaki. So offsets are a very big part of the process of the industry. So the way that offset works is completely different from Flexo and that Flex makeup of the inks. So the way an offset press works is you put the ink in here, and it's like a thick paste. The reason it's a thick paste is because it's made of oil. And the most important part of an offset ink is mineral oil. And the pigment is inside, suspended in the oil. So why is that? Well, that's because the offset process relies upon the separation between ink and water. Okay, so I did that sort of thing at school where you put oil in a water tank and oil floats. The oil floats to the top, okay, because oil and water don't like each other, okay, they separate, they shear away. So the way that the offset process works is that on the plate surface, you have two layers, and the second layer likes oil. Okay, so it's like the oil receptive layer. This top layer doesn't like oil. Okay, so the oil is going to be washed away by water from this part, but will stick to that part. So the laser comes down here and makes a hole through that top layer where you won't have your image, have your dot. And then when you run your ink in, it sticks to that part of the plate and gets washed away by the water from the other part of the plate. So it's about the repellent qualities of oil and water. That's what offset's about. So that's why the paste, that's why the ink is like it's like an oil, it's like oil paste. And very often, again, we'll come back to this when we talk more about the printing processes, but you might call offset, you often hear it called offset litho, or lithography, and lith in Latin is stone. Litho. And this is the very first printing process, like the monks used to do it. So the monks would get a stone, like a slab of stone, and they get a wax crayon. They basically wax it out, but they wanted the ink to stick, and then they roll ink over the wax and that kind of stuff. So that's where it goes back to. Okay, so and the problem is, of course, is that if you've got this thick ink paste for offset, that isn't going to go onto a plate and it isn't going to flow onto a material. So for offset, you need that ink that needs to be broken down. So you have all these like little rollers, probably about 22 rollers. So the ink gets broken down by the rollers into a liquid. So by the time it hits the plate, it's liquid. It flows onto the plate, water comes down here, and then the image, when it's finished, goes onto a rubber blanket and then onto the material. Okay, that's an offset ink. Screen printing. So screen printing is, you might have done sort of t-shirt printing. It's a very simple process. Okay, so you just get a screen, which is just a plate made of any material, mostly nickel. And where you want your image, you make holes in it. Okay, you make holes in it, and then you get a squeegee, put the ink across the top, get a squeegee, and the squeegee just forces the ink through the holes. So that's really simple. That's how to make t-shirts and kind of stuff. And you can also get screen as a rotary. You do like Stork. That's what basically what Stork do, and only Stork do, because they've basically got a monopoly in the market. So with the rotary screen, you're pumping ink into the middle of the screen. Okay, so that's in the middle. Then the squeegee, as the plate rotates, the squeegee here forces the ink through the holes in the screen. It's exactly the same process. So because you're forcing ink through the holes, it's much thicker ink. So a screen ink is somewhere between a flexo ink and an offset ink. And what that means is, because it's very thick ink, it's used typically for things like decorating wine labels. We want that really sort of thick, kind of, almost tactile, almost feel the screen ink. And you rub your finger across it. Screen's also used for putting down very heavy white. So if I'm going to print on a film, I don't want to see the product through the film. I'm going to print the screen white first. That's why we have combination printing presses. We have a screen unit, and we have a flexo unit, varnish unit. So the screen ink is kind of halfway between viscosity between a flexo ink and an offset paste. Letterpress. A letterpress process is kind of like offset and kind of like flexo. So you start off with this pasty ink again, and it gets broken down by exactly the same way as offset gets broken down by the rollers. It's a liquid, goes onto the plate. And when it's on the plate, it's like a flexo press. It just goes straight onto like a potato printing, straight onto the raised dots, straight onto the material. So letterpress ink is the same kind of consistency as offset ink. And you see the guys there who see on the presses that they'll get like a scraper. Like a kind of like a scraper knife, and they'll scrape it out and they'll actually scrape it into the where they put the ink, because it's like a trowel. Whereas with the flexo inks and screen inks, you can pump them. It's like a liquid, so you can pump it. And gravure. So gravure is not massive in the self-adhesive industry, but it is massive in shrink sleeves. You can also get it as a unit on a flexo press, and it's very, very big for long runs of also wet food labels, things like beer and things, really fast process. It's the most simple of all the print processes, but it's basically just have a little you have an ink tray here. You have this rubber roller, rolling in it. And then this cylinder, the plate cylinder, has got the images engraved into the cylinder, into a copper cylinder. So the ink finds its way into these little engraved lines and then goes from there straight onto the material. So gravure is a really, really simple process. The reason it's used in our industry is because it's super high quality. So all the top quality magazines like Vogue, News, things are all printed gravure, super high quality. Okay. So, and then inkjet. An inkjet is a really simple system. Obviously, you just have an inkjet head, and the drops come out of the inkjet head and just land on material. So really simple. An inkjet ink is almost exactly the same. In fact, it pretty much is the same chemically as a flexo ink. So about the same viscosity. It's in pretty much always similar, but it costs 1/3 more than a flexo ink. Which is one problem that the hybrid presses that use inkjet and flexo units, that's one problem they have, because the problem is that like if you buy a printer, buy a home printer, what happens is you've got to buy the inks, right? Buy HP printer, you've got to buy HP inks, and that's really expensive. And of course, HP will tell you, or whoever, that if you don't use their inks in their printer, they voids the warranty because they design it especially for the inks, blah blah blah. It's exactly the same with the inkjet inks. So chemically, is there any difference between an ink produced by EFI and an ink produced by Domino? Legally, being recorded, so it's hard to, but not much more than a very little daylight, basically. So, could you use a Domino UV ink in a Durst printer? Probably yes. But it'll avoid your warranty. Okay, so all the that sort of stuff. So when the inkjet guys talk about HP, the fact that you're locked into a system, you are. You only use HP electro inks, but it's exactly the same way. You're locked into an ink system with inkjet. There's one reason why when EFI sold its inkjet business to Zycon, they kept the rights to supply the ink. I mean, Zycon were basically, I don't know who did that deal, but it was kind of, so that's a profitable part of the business. You almost like selling the hardware is like one thing, but selling the inks is the key. Okay, so that's so they're the main print processes. And talk now briefly about, I'm trying to keep down an hour last time. So the next thing to talk about is ways of drying and curing. Okay, any questions so far?
Just the gravure one, the gravure process, you said is a very simple process, but the ink will be low viscosity as well,
that's right, like super runny, yeah. And the way that also works is that they add static electricity, because the problem is with gravure, without going into too much, is that because the cylinder is engraved with a little lines, the ink got to get into those lines. So what they do is they put like static electricity into the ink, so it kind of flies into the little chambers.
Okay.
So it needs to be some super liquid to do that. Okay, so drying curing. So as I said, the kind of key thing about any ink, it has to dry really, really quickly, and has to dry completely, and it has to be dry so completely that if you have like a rub test, immediately afterwards you can get like a coin and it won't rub off. So it's a massive challenge. And as presses get faster and faster, like inkjet gets faster, flexo gets faster, offset gets faster. But these guys are having a struggle to kind of keep up. So the main ways of drying and curing, let's start off with a water base. Okay. So water base is effectively, it's like a water ink, what do you call that? Watercolor. It's exactly the same thing. So basically you have pigments, colour pigments suspended in water. There are other additives in there, just they often have a little bit of solvent in there, a few other things. So it's not pure water, but generally speaking, it's a water-based ink. So the pigment is suspended in the water. You just heat it, like with a massive hairdryer, evaporates away the water and leaves the pigment. So really, really simple stuff. So basically, what happens if you're using watercolor paints, you need to put a hairdryer over it. Okay. So the water gets evaporated. What it leaves behind is a pigment. Solvent. Solvent is basically exactly the same system, except instead of water, it uses solvent to carry the pigments of ink. The good thing about solvent in this situation is it evaporates a lot quicker than water. Okay, so you don't need very much heat to make solvent evaporate. Oof, and it's gone. Whereas water needs a great deal more heat. So before we go on to energy curing, let's kind of look at what the challenges are in these chemistries. So challenges for water-based. So if you ever try to put a marker pen onto a carrier bag, okay, it comes straight off, right? It's exactly the same thing. If you're printing with a water-based ink onto a film, that's going to be the problem. It won't stick. It'll just roll straight off. So it's quite difficult to print water-based on film. What you have to do is you have to basically disrupt the film. So you can do that one of two ways. You can either put a coating on, special coating, so it stops being a film, it becomes something else, and the water-based can easily cling onto that special coating. If you look at a company like Memjet, so Memjet does a lot of inkjet. People like Colourdyne, and these guys, they use a Memjet head, water-based, and that's one challenge that they have. It's fine on paper because it'll grab onto the paper, no problem. Film, it slides off, so you need to have this coating. And again, when people talk about when the inkjet guys sell against HP, and they say HP needs a special coating, we don't. Well, they do. Okay, if you're a water-based inkjet, you need a special coating, or you need to hit that film really hard with an energy beam, like Corona treater or flame treater. So what the energy beam does, if you think about the surface of the film, it's really shiny. The reason it's really shiny is because it's a real high surface tension, everything's held together like that. So there's nowhere that the ink particles can kind of grab. You can grab a hold, it just slide off. So if you hit it hard with Corona, which is basically a real high energy pulse, it disrupts all the molecules. It literally breaks them up. So it creates like little handholds where the ink can just grab on. So Corona treaters, that's people like flame treaters will be Sherman treaters. These are guys, but they do basically the same thing. So it's either flame or it's a massive pulse of electrical power. So when you go and see most flexo presses today, most printers print film, PS labels with the film top or the treat these. You've got to have these Corona treaters in the front. So the other problem with water-based is, as we said before, water takes a lot of energy to evaporate, especially these kind of press speeds, 150 meters a minute, 750, 250 meters a minute, 450 feet. So you've got to have an awful lot of power. So what you see with these machines is that, okay, so if you've got a narrow web press, so what we're used to seeing is that's a print unit here, print unit there, and the UV dryer will just be there. Okay, like a little lamp will just be there, and material comes through here, goes past the lamp, and the UV lamp dries it directly. With water-based, they have to have enough room, enough space for that to dry with the air. So you can always tell a press it's got water-based ink because if that's a print unit, it'll have like a transport rope up here and down again. And here they'll have like a massive great hair dryer. They're using infrared or blowing hot air into the web as it goes up, as it goes down again. So the water-based inks take a lot of power to dry, and that's environmentally, it's also a bit of an issue. So when you see the big CI presses, when you get bigger, big central impression presses, okay, like Wiman, Holshaw, like a Comex-E. So there you've got the big central impression drum, you've got your brick units around the drum. The materials coming in here, then you've got a massive, great big drying tunnel like that. So that's why the presses look like they do. So material comes in here, goes around the drum, then goes right through this big drying tunnel, and a massive great gas oven things, and then it gets rewound at the other end when it's drying. So one of the issues with central impression using water-based is that a massive amount of energy goes into drying the inks. Okay, so that's water-based. Solvent. Okay, so as I said, the good thing about solvent from a sustainability point of view is that you don't need nearly as much heat to evaporate the solvent. So you still have a kind of similar system. You still have the dryers, but I need much less energy. And machines can run faster with solvent because it's much easier to dissolve away the solvent and just leave the pigment. Okay, what are the downsides of solvent? Well, downside of solvent is that it's a global warming gas, CO2 emissions, and everybody wants to get rid of it. So the Chinese government have just basically, well, they haven't quite banned it, but they're close to banning it, which is why the Chinese government is calling it Flexo now. Yeah, so what we have to do on a solvent press, say that's a solvent machine there, is you have to have a hood above the unit. So when the solvent gets evaporated, it goes into the hood. It can't go out to the environment. And you can either burn it or you can recycle it. So you can take that solvent and you can put it back into a tank, and where it becomes solvent again, it's liquid again, and you can sell it back to the ink manufacturer, or you can use it in some other way. So the expense of solvent is that you've got to have this solvent recovery system as well as a heating system on the press. And I've even seen cases where they're using more energy to actually burn the stuff in here than they are to actually operate the press. So, right. The other issue with solvents, so important for Ladle Expo, we had the issue at the China show, was that they're highly flammable. Okay, so you don't put a match anywhere near a solvent ink and it will explode. Basically, it's like petrol, what it is. So health and safety are massive issues for solvents. So if anybody has a solvent unit at Ladle Expo, or they're using solvent anyway, they're going to have explosion-proof cabinets. The problem we had in Asia, the China show, was that it was a Chinese screen printing company, and they were washing their plates with solvents. And somebody from Dow spotted this can of solvents at the back of the stand and photographed it. And next thing we know is Dow were ringing the environmental police, from Shanghai environmental police. So then we always had a fight because the guys wouldn't throw it away, and Daniel heroically threw himself in the middle of these two war insects like kung fu guys. It was great. It was really spectacular. But it shows the problem. You can't have.
Atrocious, though, wasn't it?
Yes.
The smell was just. It gave every everyone had headaches, didn't it?
Yeah. It's no longer gone. That's but also, we can't have it in a show. So it's worth bearing in mind that some people, although they might not have a solvent press, they might be using solvents to clean the press down. Things like what's happened here, wasn't it?
Yeah.
So Andy, with solvent inks, can solvent inks be used on food packaging, anything to do with food?
Right. Really important. And I'll come to that now. So we're talk about UV now. And one of the big problems with UV that we've heard about is migration. Okay, so I'll explain why that happens in a sec. But the reason that water-based and solvents are useful for all food packaging, all flexible packaging, there's nothing left. Once the once the water's gone, the solvent's gone, evaporated, all that's left is a colour, pigments. So there's nothing left to contaminate food or drink. So it's pretty much a safe process for food. The only thing that can go wrong with solvents is that, you know, solvents is carcinogenic, it's explosive, it's very, very evil, nasty stuff. So you don't want that being in the packaging anywhere near food. So what they do on a solvent press, okay, so let's use it as a solvent press here. They're using solvent inks. So they've got the explosion-proof cabinet all around the press. They've got these big dryers here, so when the web's going through the tunnel, the dryers are going away like this. And here, where they're rewinding the material, they take a random sample. So every I don't know, 1,000 meters, they'll stop the machine and take a sample. They'll put that sample into an oven, and they'll see whether any solvent comes out of it. Because if you have anything wrong with your ovens, the solvent is not going to leave the material, it's going to stain the material, and that's like very, very nasty. So that's the way they test it. It's a little bit hit and miss. And this is Federico's point. I'll come back to it later. So Federico's point at Bob's is that, we'll talk about you in just a sec, but he says solvents are actually, although everybody uses it, technically, potentially, it's dangerous, because how do you know that in the next 10 yards after you've measured that little bit of sample, that the gas is not spiking the gas levels, or gas levels are going to go down, or the ambient temperature changes, or somebody puts in the fresh set of inks with less solvent in it, or more solvent. So you've got no way of guaranteeing that the next 10 meters are going to be compliant as that sample that you tested was. So in reality, no one's ever died of having solvent in a pack. You know, every time that you fill your car up with petrol, you're breathing in a zillion times more benzene than if you just sat there eating packs of flexible packaging and safe goods, you know. So, but nonetheless, very important for the brands that all the solvent is out of that pack. And if it is, it's perfectly safe. Right, UV. Okay, UV. So UV was developed in Europe back in probably the in fact it was early 1990s, because I remember we had a conference in 1992 on new UV technology. And the reason that UV is important in our industry is because it's not drying, inks don't evaporate. What happens is that they become solid. Okay, so when they get hit by ultraviolet radiation, they just become like a solid film. So imagine it's like plastic. It's not like an ink drying. It becomes physically, transforms itself into a physical skin on packaging. The way that works is so imagine that that's the surface of the material with the ink on it. Before curing, imagine like a swarm of bees. Right, so these little things like flying about, and these are called photo initiators. I'll split it out, so it's really important. Okay, so these are photo initiators. So what now I'm going to do is I'm now going to shine a UV lamp source. Right, ultraviolet is in the violet part of the spectrum, visible spectrum. Right? So when you see these lamps on the press, you always see them glowing that kind of purple colour. Okay, so you sit just outside. If you imagine the ambient spectrum, it goes from red to visible to ultraviolet to invisible. So that's where they sit. So okay, so I'm now going to hit them with a pulse of ultraviolet light. What then happens is that each of these bees then effectively gets kind of captured and bonded. So as soon as that light hits them, they bond immediately with the substrate. And it becomes a film. So it's completely different from the evaporation technologies. Nothing evaporates, it goes from being a solid to a solid. The good thing about that is it's instant. So as soon as that UV hits those photoinitiators, bang, it's immediately cured. So you can run a press at any speed with UV. There's no limitations to the speed. The other thing is that because nothing evaporates, what you see is what you get. So the colour that you print with is the colour that you end up with. Sometimes when you print with a water-based or solvent, you get things evaporating. The final colour of it can look a little bit different from the colour you started out with, because sometimes you're seeing it through the, imagine like looking at a pond with fish in it. So you're looking at pigments through the water, and it can sort of like change the way it looks. So the water's gone, but that doesn't look quite so vibrant as it was when I saw the proof, But with UV, the colour that you see in the ink pot is exactly the same colour as you'll see on the final printed material. So another one of Federico's things about why UV is better than solvent. Okay, so for initiators, UV lamp and solid film. Now the problems arise, migration problems potentially arise, because these little bees here are super high energy, and they'll keep that energy for about probably kind of 2 or 3 days once they're printed. So they've got such high energy that they can actually dive through a label, straight through a label, and straight through a pack into the food. So if you have, let's say, Coke bottle. A label like that, and that's a PET bottle. So if you haven't completely cured the red ink, it can go through that plastic, through the container, and into the Coke. You wouldn't know, because it's carcinogenic into a carcinogen, right? But nonetheless. Back in the early 2000s, and again I remember writing the story when it happened, Nestle, so you can hear a lot about Nestle. Nestle had a baby food product, and some packaging wasn't a label, but it was what part of the packaging it was, but anyway, it wasn't cured properly, and exactly that happened. So they found in the photoinitiators, these are highly carcinogenic. They found these inside the baby food and tested it. At which point Nestle said, right, no UV at all in any of our food-based products, and everybody else followed. So UV from the kind of late 1990s and early 2000s was completely banned from food-based products. And for this reason. You can't guarantee that all these little bees are going to be battened down and all going to be squashed onto the substrate surface. Then there's a danger that it'll go through plastic. So they can go through plastic up to a thickness of Coke, so that's pretty much that. They can't go through glass, and they can't go through aluminium. So you're perfectly safe using UV as long as it's going onto a can or a bottle. Okay, so that's migration. The other thing shown at the moment on the UV side is LED UV. So these are LED lights. Sunlight's got a lot of LED in it, as well as frequencies, as well as general UV. The difference between LED and UV and standard UV is in the range of frequencies, big colours. So if you look at the spectrum, so we can see around about here, okay? What we can see outside, that's the visible part of the spectrum. So here you're going towards the ultraviolet, and here you're going towards the infrared. That's the infrared, that's the red, and that's towards the blue, purple, ultraviolet. Okay, so A UV ink will, the lamp throws out energy across this whole spectrum. So when you're designing an ink, it just has to fit somewhere of this. It doesn't have to be cured by any one of this, like this quite wide band of UV spectrum. The LED, on the other hand, so that's again that's the spectrum again, visible, that's UV. It only uses one very narrow wavelength of the UV. It's almost like a kind of little focused beam. Okay. So what that means is that when you design the ink has to be only sensitive to that one very small wavelength. So it's much easier to design a UV ink with a standard lamp. The LED you could develop specially, it's slightly more expensive. The advantages of LED. So the first advantage is that a standard UV lamp is giving out all this broad range of energy is manufactured with mercury. So what you do is you excite the mercury with electrical pulse, and it radiates a whole broad band of UV light, and that's what cures the ink. Mercury is a poison. It's now been banned by the EU. So mercury is like solvent, it's not on its way out. So UV lamps have the EU and the US FDA has given them an extended life, as long as they're just disposed of properly. You can't just put them in a landfill. Mercury is super poisonous. So in the long run, these lamps are gone. And you'll sometimes hear them called arc, sometimes hear them called mercury. So yeah, they just use this arc electricity to stimulate the mercury lamp. So LED from that point of view, these are LEDs. They're just a little lamp, a little light you get here, or on the watch, or in a... Okay, so the other advantage of LED is that yeah, we'll come back to this when we talk more about process technology later. But as soon as the LED is turned on, it immediately cures, then you turn it off again. Okay, with the arc lamps, it takes a little long time for them to warm up and then to get cool again. So a lot of energy is being used up while it's happening. So LED lights are super energy efficient. Okay. So briefly about low migration. So the problem that we saw with all UV, including LED, is the danger of the photoinitiators. The LED still uses photoinitiators as the buzzy bees, but they're along, like buzzy bees just on a very sort of narrow spectrum of buzzy bees. Okay, rather than with the arc lamps, they're like right across there. So it still uses photoinitiators, so there's still the danger with an LED that these little bees are going to go straight through, die through the packaging. So what's the industry done about it? Okay, so low migration. So one thing that they've done is a very kind of simple thing. They said, if that is the photoinitiator and it's going through this bit of plastic, if you look at it on the kind of microscopic level, there are these molecules of plastic. And this thing is going right between the molecules into the food. So basically, if we can make this particle bigger, then physically it can't go through those holes in the molecules in the plastic. So one approach to low migration is they just try to make the photoinitiators bigger. The other approach is you try to make them more reactive. So when you basically put more of them into a small space, so they're more likely to cure completely. So two approaches: you make them bigger and you make them more reactive, make them more expensive. So these low migration inks are going to be about, I don't know, I think Nicholas told me they're about another third more expensive than the standard. So if you go to a place like OPM in these, he's using Denon Gemelli low migration inks for exactly this reason. He does a lot of flexible packaging. Right, so that's migration. Okay, so let's talk ever so briefly then, quick 5 minutes about some other kind of issues around inks. Colour mixing, colour matching. Again, so we're going to come back to this in more detail when we talk about print processes, but there are two main types of it. There's a spot colour ink, spot colour, and there is the process colour. Right. Okay, so a spot colour, you might also hear this called a solid ink. So let's say that I'm Cadbury's, and it's my Cadbury's purple. It's my brand. And our eyes are super sensitive to colour. And very slight deviations. Those of you who were, last one we did a talk last year about colour, there was a thing called delta E. So delta E measures when the human eye can see a colour difference between two samples. And the delta series goes from 1 to 5. About 1 to 3, over 3, you'll start to see a colour shift. So what brands are very nervous about is having two inks that are kind of Cadbury's purple, but slightly different. So they will certify a Cadbury's purple. And if you print for Cadbury's, you've got to use that purple. Okay, so we call that spot colour. Sometimes you'll hear it called a solid colour. It's the same for Coca-Cola Red, for for any kind of brand colour where they have 100%. Process colour. So that's when you're using more than one colour to make another colour. Obviously, the problem with spot colours is if you've got a label with 20 colours in, you can't have 20 colours, 20 inks, because you've only got, most presses got 6 or 8 print stations. Okay, so you've got to be able to make every colour out of 6 or out of 8. So inks come as standard in cyan, magenta, yellow and black. We use the word K for black. It means key, like the key lines. So basically it's different combinations of those 4 colours make up any other colour. And if you want to be able to use more colours, then you add orange, green and violet. So you'll often hear press manufacturers talk about extended colour gamut inks. That's what that is. So if you look at cyan, magenta, yellow and black, imagine like a kind of ball of colour. Okay, that'll get you so far, but you can't get orange, green or violet using those 4 colours. Just the colours different. So if you want to if your label's got loads of green in it, then you're probably going to want to add an extra green unit to these 4 colours. So like all the HP Indigo presses, they're all, and most inkjet now is same colour. Okay, so, and finally, so look at the difference between these and the HP Indigo ink. So the HP Indigo, they call their inks electro inks. Okay, electro inks. And an electro ink is kind of like, it kind of feels like an offset ink. So it's mineral oil and you've got the pigment suspended in the oil. So it looks like an offset ink. And the way it differs is that the ink pigments within the ink. So these are they're kind of sensitive to electrostatic charges. Okay, so here's my drum, here's my plate. And what the Indigo system does is it hasn't used a laser. So where you're going to want your images, it just sensitizes that part of the plate. And these little sensitized particles fly onto it. Okay, so that's your cyan, so that's your magenta. That's where I want my magenta. So the laser sensitizes it, and the little particles fly onto that spot. And you transfer that onto a printing blanket, and that goes onto the material. So the HP Indigo, they like to call it digital offset, because it kind of looks like an oxide. You've got pigment suspended in mineral oil, but it operates in a completely different way to oxide and oxide. And whilst toner systems don't really come to the inks category, but if you've got Zycon, toner presses, or any of the fusion presses, so who else will do that? Konica Minolta can do it as well. So that's basically just like a photocopy. You're taking little sort of particles of ink, like toner particles, and you're fusing it by heat onto the substrate. Okay, and that's it. That's the inks. So are there any questions?
The biggest challenge for them is then recycling in the environment, isn't it? Inks in general. That's the biggest challenge for them.
Yeah. So the issues with recycling. Yeah. It's a little bit of an unknown at the moment.
It's them in this room.
Right, I'm done. Right, so yeah, it's potentially UV might be a problem because it bonds to the label. You can't separate it out. But yeah, but so far the actual ink themselves is a tiny part of the actual label that they're not showing it and the impact on the recycling system. Good.
Thank you, Annie.
Thank you.
Thank you.